Okay, so let's try some functions here. Okay, and so we want to print all the nodes in the linked list. That's what we want here. So let's assume that we want to implement the print functions in the previous slide class. Okay, and then we declare one list node pointer car. Basically, it means a current pointer. And in the for loop, let's assume that head is pointing the linked list like this in this graph. Head is pointing the first element, and then the first node's link is pointing the second node, and second node's link is pointing the third node, and the third node is pointing the fourth, and the fourth is the last one because the third node's pointer is null. Okay, so something like a character array to represent a string, so that in the character array we need the null pointer, null character all the time, indicating the end of the string. Likewise, in the linked list, the last node should have a null pointer, indicating that is the last node. Okay, so head is pointing this linked list, and then the car gets head. So car starts from head. Okay, don't get confused. Head is a pointer and car is a pointer. So head has the address of the first node. Let's say in this example, the value of head is the address of the bat node. Okay, and then car will get that, which means the car is pointing the bat node. Okay, and then in the for loop, in the second statement, car is not null. It means as long as car is not null, then we will iterate this for loop. Okay, and then the last, car is car link. Okay, so car will be updated with car link. Okay, so look at this figure. So when the car is pointing the first node, okay, what is the car link? Car link has the address of cat node. Okay, so again, the value of a car is the address of bat node, the first node, and the car link means the first node's link. Okay, so the first node's link has the address of the second node or the cat node. So car is car link means the car is pointing the second node. Okay, and then if we repeat, then car will point to the next node and the next node. So in this way, we can traverse this linked list. So while we are iterating with this for loop, if we print out the car data, then we will print out bat and cat and set and vet in that order. Are you following me? So this is the simplest operations with the linked list. Okay, again, head is pointing this linked list. Okay, initially, you might be confused with these operations basically. So in the class, head is a pointer. Okay, and then whenever we add a new element, then we allocate memory space, and then head will point that first node. Okay, when we add another element, then we will allocate memory space, and then the first node's link will point to that memory space. So that's how we add all the elements. Okay, so we'll talk about that later. So let's assume that this head is pointing one linked list. Okay, so we will talk about the insertion operation later from the empty list. So if we have a linked list and head is pointing that linked list, which means head is pointing the first node of this linked list, or the value of head is the address of the first node. Okay, then we can traverse this linked list in this way. Okay, still we are assuming that we have a linked list and head is pointing the first element of the linked list. Okay, now in this slide we are interested in another operations to find an element. Okay, So we will follow the link from head pointer head until the target node is found. Okay, and then the computational cost is len, the linear to len. The len is the length of the linked list. Okay, so let's start from head. So in the for loop, core is from head, and then we iterate this for loop as long as core is not null, and core is moving to the next node. Okay, so let's assume that we are looking for a set in the third structure, set. Okay, then let's follow this for loop, and then look at the figure at the same time too. Okay, and the core is pointing the first node, and core is not null, so we go into this for loop, and then we check if the data is a set, and which is not the case, then we move to the next node. So now core is pointing the second node, the can node. Okay, and then we check if it is a set, which is not the case, then we move to the next one. So now core is pointing a set node, the third node, and then when we check if this data is the same as the set, which is the case, so we found it, we break. Okay, so after this for loop, then we will check if core is null or not. If core is not null, like this, if core is not null, it means we quit this for loop because we found it, and the core is actually pointing that node. Okay, so as long as core is not null, then we found it, and core is pointing that node. But what if we are looking for like a FAT, F-A-T? So we don't have FAT in this linked list. Okay, then when we check the set, which is not the case. Okay, so when the core is pointing the third node, which is not the same as FAT, so we move to the next one, VAT. Okay, so core is pointing the fourth node. So when we compare the VAT to a FAT, then they are different. Then core will move to the next node. Okay, so this is a little tricky. Core will be core link. Okay, so core link is actually a null here. Then core will be null. Okay, so the core is null, which means we quit this for loop. Okay, so after this for loop, if the core is null, then we couldn't find our target in this linked list. Okay, when the target is FAT, then we couldn't find it, and the core is null. Okay, so if core is null, it means we quit this for loop because core is null. It means we couldn't quit from this break statement, which means we couldn't find it. Okay, and we have a little different operation here. So instead of finding the target element, we want to find the nth element. So what do we have in the nth element? Okay, so follow the link from the head pointer n times. Okay, so core is a list node pointer, and we have another integer variable I. Okay, then the core starts from head, and I start from 0 in this for loop, and then core. So we will iterate this for loop as long as core is not null and as long as I is less than n. Okay, and then core is moving to the next node, and then I increases by 1. Okay, and then we don't have to do anything in this for loop. Okay, and then after this for loop, we will check if core is null or not. If core is null, what does that mean? If core is null, it means we quit this for loop because core was null. Okay, it means we don't have n elements in the linked list. So when we have 4 elements, then the n is 5 or 6. Then we have to quit when the core is null. So if at the end of this, after this for loop, if core is null, then we don't have n elements in the linked list. Okay. But if core is not null, it means we quit this for loop because n is equal to I is equal to n. Okay. So we will quit this for loop. Either core is null or I is n. Okay. So if core is not null, it means I is n. And if I is n, it means we have nth element in the linked list, and core is actually pointing that node. And core is not null, definitely. Okay. Okay, now we have insertion operation. So far, we assume that we have a beautiful linked list. Okay, so now let's talk about how to make it. Okay, so first, we will insert a new node after a node PTR. So let's assume that the PTR is pointing some node. Okay, then how do we know? Okay, we can retrieve. Okay, we can find cat from this linked list, and then we want to insert a new node right after cat node and right before the set node. Okay, so the PTR is pointing cat in this graph. Okay, and then we want to insert mat right after cat. Then we have a couple of steps here. First, we have to allocate memory space for the new node, obviously. Okay, so whenever we add a new node, then we have to allocate memory space. Okay, and then next we have to set the data fields of the new node. Okay, in this example, the data field is a string, and then we set the mat. Mat is the data of the new node. And then next, now we have to change the pointers. Okay, the third step, we will set the new node link to address found in the link of PTR, which means the new node link will get PTR link. You know what I'm saying? PTR is pointing set. Now the new node link should point set. So we will copy the PTR link to new node link. Okay, now new node link is pointing set. Okay, then the last one is to set link of PTR node to new node. Okay, so can you see this from this figure? Okay, so we change the mat link pointing the set node, and then we have to move this PTR link from set node to mat node. Okay, so now if we follow this linked list from head, we have a bat and cat and mat and set and vet. Okay, cat node is pointing mat node, and mat node is pointing set node. And the other nodes are the same as before, so we don't touch the other nodes. If we have like 1000 nodes in the linked list, then we don't change the other nodes. We just touch this cat node link. Okay, that's the beauty of this linked list. Again, we allocate memory space for the new node, and the new node link will point what PTR node is pointing, and then PTR node should point the new node. Okay, then we actually just inserted a new node in the middle of cat and set. And we can implement that insertion algorithms like this. Okay, so let's assume that we use the C++ style. So instead of using malloc, we can use just the new. Okay, basically it's the same thing. Okay, if you know how malloc works, then just use new. So just to change this style. Okay, and then new node is list node pointer. Okay, and then we allocate memory space for new node. Okay, with new operator. Okay, so now new node is pointing a memory space, and then new node data will get mat. Okay, so we set the data field, and then next, the third step, new node link will get PTR link. Actually, PTR is pointing set. PTR is pointing cat, and PTR link is pointing set. So now new node link is pointing a set. Okay, the third step. And then last step, now PTR link will point to new node. Okay, quite simple, right? So you have to use this one in our class. Now we have an implementation of this insert functions as a member function of dlist class. So we had a definition of dlist class before. Okay, so now we have an implementation here. So as we've seen in the previous slide, we can use the same lines here. The new node is a list node pointer, and then we allocate memory space, and then we set the data field, and the new node link will point the next one, and the head is actually is corresponding to PTR in the previous slide, and then head will point the new node. Okay, next operation is a deletion, which is quite important too. Okay, so deleting a node is quite simple too. So we don't have to shift anything. We have to deallocate one node, and then we have to change the pointers. That's it. Okay, first find an element, immediately proceeds node to delete, say trail. Okay, so in this figure, we want to delete set node. Okay, then when we delete a set node, then we need a pointer pointing cat node. Okay, that's what this first step says. Find an element, immediately precedes the node to delete. So let's say a trail. A trail is pointing the previous node. Okay, and then set trail link to link of the node to delete. So we are talking about this red arrow. So set link is pointing that, and the cat link will point that, which is the node that the set is pointing. Okay, and then so now we have a linked list from head to bat to cat to vet, jumping, skipping this set, and then now we have to deallocate the memory space for the set node. Okay, so this is quite simple. Okay, so we have to have a pointer pointing the previous node. Okay, and then we have to change the link of the previous node, and then we have to deallocate the memory space for the node to delete. That's it. And remember, all the time, when we delete, then we need a pointer to previous node. So we will get back to this point later. So let's implement these algorithms. Okay, so let's assume that the trail, we found this trail pointer. So trail pointer is pointing the previous node. So in this figure, so we want to delete the set, but now trail is pointing cat. Okay, then trail link should have a node to delete link. Okay, now we have a red arrow from cat to vet. Okay, and then we have to deallocate memory space for the node to delete. So just use the delete functions. Okay, the algorithm is quite simple, but when we implement these delete functions, then we have to find the previous node first. Okay, so in this implementation, we have two kind of parts. First one is to find the previous node, and the second part is actually to change the link and deallocate memory space. Okay, so let's take a look at this implementation line by line. Okay, so we have one list node pointer prev, which is supposed to be pointing the previous node. So we'll talk about it later. And then the second pointer is current. So current is actually starting from head. Okay, so current is pointing the first node of the linked list. Okay, now let's find the previous node. So current node is, so with this while loop, current node is actually, it is checking if it has the data, the target data. Okay, we have to find this target data, then we will delete that node. Okay, so we check if it has the target data. If that's not the case, then before current pointer moves to the next node, then prev will point what current is pointing now. Okay, so prev is basically following the current pointer. So current pointer is moving to the next node, and then prev is following the current node. Okay, one step behind. So if we quit this while loop, then the current is pointing the target node and prev is pointing the previous node. Okay, good. So now if current is not null, so if current is pointing something, it means we have the target node. Okay, and then we will delete. If current is null, that means we don't have the target node there, so we cannot delete. Let's say we want to delete the set from the linked list, then we can delete. But if we want to delete a fact which is not there, then we cannot delete anything, so we just finish this function. So we check if current is null or not. If current is not null, then this implementation is a little tricky. So we have two different cases. If current is head, it means the target node is the first node of this linked list. Okay, if it is the first node, okay, then head is pointing the second node. So we assign the current link to head. It means current link is pointing the second node. Okay, again, if current is the same as head, it means current is pointing the first node. So now current link is pointing the second node. Now head is pointing the second node. Okay, and then we delete the first node. Okay, that's the algorithm. Okay, second, if current is not head, so it means current is pointing somewhere in the middle of this linked list. Okay, then prev link will point the current link. Okay, so we have a current node, and we have a prev and current and the current link, and the prev link will point to the current link. So originally prev link was pointing the current node. Okay, so now prev link is pointing the current link, skipping the current, and then we delete current. Okay, that's it. So in the previous slide, with the figures, we saw this else part. So when the current is not the head, then prev link is pointing the current link, then we delete current. But that's not it. We have to check if current is pointing the first node, and then we have to implement for that case. So that's what we have here. If the current is head, then we don't have a prev, right? We don't have prev point is pointing something. It's pointing just garbage. Okay. Instead, we just move this head to point the second node, and then we delete the current node. Okay, that's it. Okay, next, operations are quite simple operations. So creating an empty linked list is quite simple. So after declaring this list node pointer head, so we just assign null. So head is pointing nothing. Okay, that is a simple way to create an empty linked list. So this one will go into the constructor of the dList class. Okay, and then next one, empty check. So is empty, a function can be implemented simply. So we return PTR we just check if PTR is null. If PTR is null, then we will return true. If PTR is not null, then we will return false. Okay, so this one is not C++ style, but you know how to translate this one into the C++ member functions. Okay, so we don't have to pass any parameter there. So we just check if head is null. If head is null, then it is empty. Otherwise, it's not empty. Okay, so we don't have to pass any parameters in if this is empty is a member function of the list class. Okay, destructor is a little complicated. Okay, So destructor is supposed to deallocate all the memory space. Okay, so the name of this destructor is tilde_dlist. Basically, if the class name is dlist and the destructor name is tilde_dlist, okay, and then I implemented this destructor in this way. So we just call delete list function passing head. Okay, and then in the delete list functions, actually, when we have a linked list, then there's an order to deallocate memory space. Okay, if we delete the first node, then how do we know how to point to the second, how to have an access to the second node? Okay, so we want to deallocate memory space of the last node first, and then the second to the last, and then third to the last. Okay, so we will deallocate memory space from the last node to the first node. Okay. If you want to deallocate memory space from the first node to the last node, we can do that too. Okay, then before deallocating memory space of the first node, then we have to copy the pointer to the second node. Okay, and then we deallocate memory space, and then we go to the second node, and then before deallocating the memory space for the second node, then we have to copy the link to the third node. Okay, and then we deallocate the second node, and then we go to the third node. Okay, you can do that. But in these implementations, I used two different approaches: recursive approach and iterative approach. In recursive approach, if the node PTR is not null, then we call delete list functions passing node PTR link. So as long as node PTR is not null, then we call delete list with next node and the next node and the next node. And then if this node is the last node, then we will actually deallocate that node PTR. Okay, and then we deallocate and deallocate. So basically we deallocate the nodes from the last one to the first one. Or in the second part of this slide, we have a destructor without delete list functions. We actually deallocate memory space in an iterative approach. Okay, so we have current head. We have a list node pointer current, which is pointing the head, and then we have next. So if the current is not null, then next is pointing the next of the current node, and then we delete the current node, and the current is moving to the next. So that's what I said before. So we can deallocate all the nodes from the first node to the last node in that order with an iterative approach. We can think of other operations. The first one is to get length in this slide. So get length of this of the linked list is quite simple. So we start from the head, and then until we meet the null, then we just move to the next node and the next node. And while we move to the next node, we increase the integer variable n. N start from 0. Okay, so we increase n whenever we move to the next one. So that's it. So we just return the n. Okay, that's simple. And next one is inverting the list. So it means, when we have a linked list, then we can change the order. So the last one will be the first one, and the second to the last one will be the second one, etc. So this one is not that simple. So let me explain how to implement this one. Okay, so first we check if it is empty. If it is empty, then there's nothing to invert, so just we return. And then we declare two pointers, current and the next. And current points the node that head is pointing. So it means actually initially current is pointing the first node, and then the next is pointing the second node. Or if we have just only one node, then the next will be just a null. Okay, so as long as at least we have one node here because it is not empty. So core is pointing the first node, and the next is pointing the next node or the null. Okay, So in the while loop, so as long as the current is not null, obviously for the first time, so current is not null. And then we have two different cases. First, current is head. Okay, so in this graph, the red ones are corresponding to the first iterations. So current is pointing the first node and next one is pointing the second node. And if the current is the same as head, which is the case here, and then the current link will be null. So bad link will be null. Okay, so imagine that. And then current, we skip this else part, and then the current will move to the next one. Okay, and then next will move to the next one. So the bad link is null, and the current is pointing the cat, and the next is pointing set. So now the blue colored, the arrows and the car and next are indicating the second iterations. So in the second iteration of this while loop, when we check if current is head, which is not the case, head is still pointing to bad. Okay, and then in the else statement, a current link will be head. Okay, so cat link will point to bad. See what I'm saying? Cat link will point to bad, and head will point cat. Okay, so imagine that head is pointing cat and cat is pointing bad. That's what's happening here. And then core is moving to the next. So after this else statement, core is moving to the next one, and as long as the core is not null, the next is moving to the next one. So in this figure, core is in the second iteration, core is pointing the set, the last node, and the next will be null. Okay, that's it. So in the third iterations, we will move, changing the pointers, and then we reverse the order of the linked list. That might be a little confusing, so you have to follow the lines step by step, drawing these figures, then you will figure out. Now we have a main function for dlist class. So in the main function, we declare one dlist pointer variable list. Okay, list will get a memory space with the new operator. Okay, and then list node pointer variable node is declared. Okay, so far so good. And then we call the list print function, and we call list insert function insert, and print, and invert print, and retrieve, delete print, and delete list. And the last line, when we call delete list, then it actually calls the destructor ~delist functions. Okay, and then it will deallocate all the nodes following the links. Okay, so you are supposed to implement this print and insert and invert and retrieve and all these functions. So basically, you have insert function and delete function in the slide. Okay, and then print function is almost there. You can just copy, and invert function is there, so you can copy that. And retrieve functions are already there, so you can copy that. So you can finish these implementations. Okay, let's think of two additional list operations. First one is concatenation of a linked list. Let's assume that we have two linked lists. Okay, then how can we concatenate two linked lists? The first linked list has three elements, three nodes, and the second one has two nodes. Then, based on these concatenations, the new linked list will have 5 nodes in there. Okay, so next, how can we copy a linked list? Okay, so basically, when we copy a linked list, we have to follow this linked list, and then following this linked list, we have to allocate memory space for a new node, and then we have to concatenate this new node to the previous linked list. You know what I'm saying? So this is a practice. So you can try to implement these things.